Good morning, everyone. Today we're going to talk about cyclotron motion and also the other spiral motion due to the existence of a charge with a velocity in a uniform electric field. We'll also look at the combination of the electric field and magnetic field and how is this affecting the charged particles going into that field. So let's start first with the cyclotron motion. The cyclotron motion is a circular motion that happens due to the existence of a charged particle that has a velocity perpendicular to the magnetic field. In this case, this cyclotron motion, as you can see here, due to the existence of the a charge with a velocity with the magnetic field, if you apply the right hand rule, you can see that the force would be pointing downward and it is perpendicular on the velocity. This motion is going to create a circular motion, and there are two important parameters in that motion, two important quantities that we can calculate. The first one is called the radius of the path, and the second one is the frequency of the motion. Now, this force is a centripetal force, and the equation that defines the relationship for that force with respect to the mass and the acceleration is given by Newton's law, where sigma f is indeed QVB that came from the cross product between the velocity and the magnetic field, knowing that the angle between the velocity and the magnetic field is 90 degrees. So here QVB sine 90 degrees basically gave me the maximum quantity that is QVB, and this equals to m. And here the force is a centripetal force. That's why the acceleration can be substituted as the v squared divided by the radius of the circular path that this charge is making. So rearranging this equation, I can find now the radius of this circular path to be the mass times the velocity divided by the charge of the particle times the magnetic field. The frequency can be calculated from the period here, which basically equals the circumference of this path divided by the velocity, the magnitude of the velocity. And here, in this case, the frequency can be derived knowing that the frequency is the inverse of the period here, which means that the frequency of the path that is circular in shape to complete one full circle, the frequency is QB divided by 2 pi m. Now notice that this frequency here is independent of the speed of the particle or the radius of the circle in which it moves. Now let's look at this question here. In this question, we have a positive charge, the Q, that enters a region of uniform magnetic field, B. In this case, in case A, we have two cases. In case A, the charge enters with a velocity that is entirely perpendicular to the field. And in case B here, I have the charge enters the field with a velocity that has a component perpendicular. So now this is can be decomposed into two components. The first component here is perpendicular that I'm going to call V perpendicular, and the second component here is parallel to the magnetic field that I will call VZ. So those are the two components of the velocity. One of them is perpendicular, which is the V perpendicular, and the second one is parallel to Z, which is VZ here. For these two cases, the charge Q follows. I have A, B, C, D, E. I need to pick the correct one. So a circular path in the xz plane in both cases. So here, what what A is saying that I have a circular path in the xz. This is the xz plane in both cases. Well, this is not completely correct. This is partially correct. Yes, there is a motion that's happening here. The circular motion for case A is happening in the xz. The same thing for the perpendicular component of the velocity is doing the circular motion along in the z in the xz plane. However, this is not completely true in the case of B. This is true for case A, but not in case B. So case A is not correct. B, a circular path in the xy plane, in this plane, which is wrong. Why? Because if you apply the right hand rule for case A, for example, you can see where V is going, uh, where V is the direction of the index finger, and B pointing up is the direction of the middle finger. Then the force F would be pointing out of the page. So here the force F is in this direction, which means that the the charge is going to make a circular motion such that it is in the xz plane. Same thing here is going to happen to the perpendicular component. It will make a circular motion that is in the xz plane. However, there's another motion that's happening along the magnetic field due to the component Vz that I have here. So B, as I said, is wrong. So circular path in the YZ plane for both cases. Again, YZ plane is wrong. The motion is not happening in the YZ or XY. The motion is happening in the XZ. So C is also wrong. Let's look at D, a circular path in the XZ plane in case A, and the spiral path with the long axis along the Y direction in case B, which is the correct one. Why? Because here the motion is going to be, so let me, case A, I have the magnetic field pointing upward, and I have the positive charge coming with a velocity that is perpendicular. And we said that the magnetic force is pointing out of the page, so like this. Now, if I am to look from the top, what am I gonna see? I will see again for case A, I will see the magnetic field is out of the page, and the charge, the velocity V this way also, and then the force would be pointing, the out of the page is going to look like this. So in order to understand this, let me put the coordinates. Let's assume that this is Z, Y, x, then this one is going to be x, y, and then z. Okay, so just to show you the top view, so this is the top view. I'm looking from the top. Right, so this is what's happening in case A. In case B, it will be different. The motion is a spiral motion. So if this is B, now case B, this is the magnetic field. I have the charge coming with an angle this way, which means this angle now can be decomposed into V perpendicular and the other V, which is the VZ. So the perpendicular one is going to be responsible for the circular motion. It will be again going in circle. And this is what's going to happen here also. It's going to go in circle within the plane. And this VZ that's going in the direction of the magnetic field is going to make it going into moving forward. So going in circles and moving forward is going to result into a spiral motion. So here it's going this way. So it is a spiral motion that is moving up this way. So the answer is D. A circular path in the XZ plane in case A, and a spiral path with the long axis along the Y direction in case B. This is a correct one. This one is also not correct. Let's look at this example. In this example, we have the following. It reads a particle with negative charge Q and a mass m equals to 2.58 10 to the power minus 15 kilograms is traveling through a region containing a uniform magnetic field. The magnetic field as a vector is given to me. At a particular moment, the velocity of the particle is given to me also, and the magnetic force on the particle has magnitude F. B equals to 1.25 Newton. Determine the magnitude of the charge. Determine the radius of curvature or cyclotron of the helical path the particle is following. Determine the pitch of the helix. The pitch is the distance traveled along the long axis of the helix per revolution. So let's solve this question here. So here we do have a magnetic field that is going in the negative direction of the Z. So let's assume that this is Z, this is Y, and this is X. So here I have magnetic field going downward and given by B equals to minus 0.12 k hat Tesla. I have the velocity as 1.05 10 to the power of 6 minus 3 I plus 4 j plus 12 k, and this is meter per second. What else? I have a magnitude of the magnetic force as 1.25 in Newton, and I also have the mass as 2.58 10 to the power minus 15 kilogram. So the velocity here has three components on the x, y, and z, right? On the x, y, and z, which means it's coming with an angle here such that it is somehow like this, has a component on the x, has a component on the y, and also has a component on the z. So now I can uh, see that this component, the one on the z, is given as this. I'll call this one Vz. So here I have Vz as 1.05 10 to the power 6 times 12 k hat. So this is on the z, which basically leaves the perpendicular component that is in the xy plane given by this times this. So I would call this one the perpendicular. The perpendicular component is 1.05 10 to the power 6 times minus 3I plus 4J meter per second. This component is the one that is responsible for the circular motion, the perpendicular, which is in the xy plane, as you can see. Why? Because the xy plane is the plane that is perpendicular on the magnetic field. So now I need to determine Q. So if I put my force, my magnetic force, that equals to Q V cross B, and then taking the V as only the perpendicular component, because that's the one that is responsible for the cyclotron motion. So the force F is, let's take the cross product here, Q, which is times 1.05 10 to the power 6 times the 0.12 of the magnetic field. Now I'll take the cross product between minus 3I plus 4J cross K hat. So here So we have here I hat, J hat, K hat, so I hat. So I hat cross K hat is going to give me minus J hat minus, so this is going to be 3, 3J, right? Then J cross K is I, so this is going to be 4 I hat. So now if I want to calculate the F magnitude is Q times 1.25 10 to the power 5 times square root of 9 plus 16. So this is the magnitude of the magnetic field. So F equals to Q times 6.25 10 to the power 5. And we know that the magnitude is 1.25. So F equals to 1.25, which means that Q is 1.25 divided by 6.25 10 to the power 5. Charge Q is 2 microcoulomb. B. Determine the radius of curvature R cyclotron. We know that this equals to mv, and this is v vertical divided by qb. So R cyclotron is, the charge is 2.58 10 to the power minus 15 times the magnitude of the vertical. So going back to the vertical, I can calculate here the magnitude to be 5.25 10 to the power 6, 5.25 10 to the power 6 divided by 2 minus 6 times the b, which is 0.12. So our cyclotron is 0.05 7 meter. C. Determine the pitch of the helix. So in order to understand what does the pitch of the helix mean, let's go back and see. Let's go back here and try to first look from the top. So if I am to look from the top, let me draw the top view there. Here I have the coordinates x, y, and z. Now if I look from the top, My Z is going to look like this, and this is my Y, and this is my X. So if I'm looking from the top, I have the magnetic field pointing downward. So the magnetic field is going to look like this. And I have the perpendicular charge. I said it has a component along the y-axis and it has a negative component along the z-axis, whereas the this is the this one is the perpendicular component. So the x is negative, which means my v perpendicular is going to look like this. So it's going like this. So having said so, then using the left hand rule, I can calculate the direction of the force. If you use your index for the velocity, your middle finger for the magnetic field that is pointing downward here, then the force would look like this, which means the motion is going to go like this in this direction. So it will look to me like as if it's a clockwise. Now I need to calculate the pitch. Now if I am to look at this again using the this axis, then I would be seeing the helical path as now the pitch is the distance from here to here. This is the pitch, the distance from here to here. I need to calculate the pitch of the helix. So, and I do have the velocity here going vz. I know the velocity, I know the time, I can calculate the distance d. So here I know that the distance is the velocity times the time, which is the period for the cyclotron motion. So this is the pitch. I know the vz. The vz here is given as 1.05 10 to the power 6 times 12k. So basically, the magnitude would be 12 times 1.05, 12.6 10 to the power 6 times the period. I need to calculate the period. So d equals 2. T cyclotron is 2 pi m divided by q b times the Vz, which is 12.6 10 to the power 6. And then if you substitute The mass is 2.58 10 to the power minus 15 divided by 2 10 to the power minus 6 and 0.12, and then pitch would be 0.86 meter. So the solution also, as mentioned here, added to you in this slide. Now, this spiral motion is what we're seeing at the aurora borealis here due to the energized particles that's coming from the sun colliding with the particles of the Earth's atmosphere causes those phenomenon going in a spiral path along those magnetic fields, causing what we call the aurora borealis. So what's happening here is those particles, they come with a velocity that is having an angle with the magnetic field, and that's why the velocity will be decomposed into two components. One of them is perpendicular on the magnetic field, and the second one is not. And this is what why the particles are going in a spiral path along the magnetic field. Comes with two components. One of them is perpendicular, and the second one is along the magnetic field. The one that is along the magnetic field will cause the particle to move along the magnetic field, while the perpendicular one will cause the particle to go in circular motion, in the cyclotron motion. Then, if you add both of them, it will give you the spiral motion. Now, if we look at the difference between the electric field and the magnetic field, if you recall, the electric field is either parallel or anti-parallel to the force, or the force is either anti-parallel or parallel with the magnetic field based on the charge itself. If it's a positive, then it is parallel. If it's a negative, then the force is anti-parallel. That's what we're seeing here for this positive charge. Now, for the magnetic field, it's different. So both of them are coming with the same velocity, as you can see. However, one of them is in the electric field, and the second one is in a magnetic field. Now, in the magnetic field, if you apply the right-hand rule, you have the velocity going in the index, you have the magnetic field pointing downward, then definitely the force would be pointing into the page. So in this case, this is the force, and the circular motion now is going to happen within the plane that is perpendicular to the magnetic field. So if I'm looking now at the total force applied on a particle in the existence of both fields, it will be the summation of both vectors. So the total F, if I have a charge that does exist within two fields at the same time, if I have magnetic field and electric field, and I have a charge that is going with a velocity, then on that charge I have an electric field, and I also have a magnetic field because my charge is moving. So the summation to them would be QE plus QV cross B. If I take the Q outside, I will get the, the total electric, the total force given as Q times between two parentheses A plus V cross B. We have what's called the velocity selector, and this velocity selector, as you can see, I have both fields at the same time. I have the electric field pointing downward. I have the magnetic field into the page, which means if I have a charge, positive charge that is coming in this direction, then this positive charge, once it's here, it will now see two forces. Since it's a positive charge, then the electric field force is going to point toward the same direction of parallel to the electric field. So let me call this one Fe. And then there's a magnetic force that is based on the right hand rule. It will be pointing upward. So theoretically, those forces are in the opposite direction. Now, do I have a value such that will make those two forces equal and canceling each other such that this charge is going to show up right here without deflecting up or down? The answer to this is yes. So if I equate the magnitude of the electric force and the magnitude of the magnetic force, which basically going to give me QE equals to QVB, right? Then in this case, the velocity, the magnitude of the velocity that's give me that the ratio of the magnitude of the electric field to the magnitude of the magnetic field. So if I have here particles with different velocities, right? Then based on my tuning, I can tune the electric field and the magnetic field such that the particles that will show up have the velocity that I am interested in. Now, if I use this velocity selector with this device that allow me to measure the radius of the cyclotron motion, then I have what's called the mass spectrometry. The mass spectrometry, I can, with a velocity selector, I can adjust the magnetic field such that I'm getting here the particles with the velocity that I want. Then after I measure the radius here of the cyclotron motion, I can work out this equation now such that I have the charge to the mass ratio. Then if I measure the R cyclotron from here, this is the distance of the radius. This is the distance of the R cyclotron. Then I can calculate the ratio between the charge to the mass, of course, knowing the velocity that I have selected already here. Mass spectrometry is an important tool in chemistry and biochemistry. We can adjust the magnetic field such that we can select the velocity of the particles that shows up at the output of the velocity selector, and then we can measure the radius of the cyclotron motion in order to identify the mass of the particle, knowing the charges on those particles, as you saw from the previous slide. So here we have the ion source where we're throwing the particles, charged particles with different masses. I can select the particles with the velocity that I want to pass through here, and then once it passes through here, it can then deflect using the magnetic force. You have a velocity here for those charges going in the index finger. Magnetic field is pointing into the page, then the force is pointing upward, and that's why you will see the cyclotron motion curling upward this way. Then by measuring the R cyclotron, I can calculate the ratio, of course knowing the velocity here from this ratio, substituting it in here. Then I can come up now with this relationship that basically gives me the relationship between the mass and the charge. If I know the charge, then I can calculate the mass. So I will measure the IR cyclotron. I have selected the velocity that I want. I know the charges for those mass, then I can calculate the mass for those charges. Now, in this example, we have an electron that is accelerated through a potential difference of 500 volt and then injected into a uniform magnetic field. Once in the field, it completes half a revolution in 2 nanoseconds. What is the radius of its motion in the field? So in this case, we know that half the period, the cyclotron motion is 2 nanoseconds. I also know delta V to be 500 volts, and here is so delta V is 500, and I have an electron that is accelerated, which means the FE is the following, and then injected into, so we can, then will be injected into a magnetic field that is perpendicular on this magnetic field, uniform magnetic field. We need to calculate the R cyclotron. We know that this is magnetic field, uniform magnetic field. So in this case, what we care about is indeed that it is perpendicular here. So the first thing we need to calculate the V. So in order to calculate the V, I know that here it's starting from rest. So this is point 1, this is point 2, or you can say this is the initial and this is the final destination. So so I know that delta U equals to minus delta K. This is going to be my reference point. If this is 0, then right here as U2 would be a negative value because the charge is going in the same direction, the displacement is in the same direction of the electric force. That's why the electric potential energy at this point will be less than the starting point. So I know U2 minus U1 equals to minus K2 minus K1. So here I know starting from the rest, so K1 is 0. So this one is 0. This one is my reference. So what do I have here? I have U2 equals to minus K2. So here U2 is, because it is less than U1, then it will be minus Q delta V. So if you take this one as magnitude, equals to minus K2, or 1.602 10 to the power minus 19 times 500 equals to half m, which is 9.1 10 to the power minus 31 times v squared. And now v equals to 1.33 10 to the power 7 meter per second. So this is my V. Now after I found my V, I need R cyclotron, which equals to MV divided by QB, right? I know Q, I know M, I know V, I need B. Where do I get B from? Well, F cyclotron equals to QB divided by 2 pi M, or B equals to 2 pi M F cyclotron divided by Q. Now this one is M over Q T cyclotron, which is 4 nanosecond. Half of the period is 2, full period is 4, so B is 2 pi times 9.1 10 to the power minus 31 divided by 1.602 10 to the power minus 19 times 4 nanoseconds, which means the magnetic field is 8.94 10 to the power minus 3 Tesla. And now take this one and substitute it here. I get R cyclotron equals to 8.47 millimeter.